Hello everyone and welcome back to NL 582, Modeling and Control of Electric Machines and Drives. And this is tutorial number 6. And we'll be dealing today with the equivalent circuit of three-phase induction motor. So the last tutorial we've been talking about the determination of the equivalent circuit parameters of the three-phase induction motor using the tests, the DC test, log rotor test, and no load test. We've been dealing with this last time. If you have those experimental readings, how you can use it to find the equivalent circuit parameters. For today, we'll be assuming we have these equivalent circuit parameters and then use it to predict the performance of the machine by solving the equivalent circuit actually. So you can have this type or this type of problems on your exams, and if you just face a very bad one, you have them both combined. That means you'll have your inputs as the experimental data, and then you use it to find the equivalent circuit parameters, and then use these parameters to solve the equivalent circuit and find the machine's performance. But this will be a very big problem. Okay, so for now, assuming we have these parameters as inputs, okay, and see what we can do with it. Okay, so yeah. And this problem is saying I have a 480 volt, 60 hertz, 6 poles, 3-phase delta connected induction motor. Like we know at the beginning, so the data is given at the very first, at the beginning of the problem, the ratings of the machine. So the rated values of the machine working at. I did the 480 volts, that is the rated voltage applied to your stator. And again, if it's not otherwise stated, that means that is the line to line voltage. Okay. That is the rated value of the line to line voltage, not the phase voltage. 60 hertz is your frequency. Again, it can be missing, and that doesn't mean you have anything missing in the problem, because you assume you're working with the frequency of the public grid in your area. So here in North America, we're talking about 60 hertz, and pretty much every other place in the world it will be 50 hertz. So yeah, at 60 hertz can be given, can be missing, but you know it, you don't need to have it. Okay. 6 poles, the number of poles in the machine, 3-phase, delta connected, that's good to have. Again, if it is not stated, it will be Y connected by default, but it's now stated that it's delta connected. Induction motor, and here's have the following parameters. It's giving you here the per phase equivalent circuit parameters: R1, R2, X1, X2, and XM. Okay. For the first glimpse, RC is not given, so let's continue with the problem. Rotational losses are 1300 watts. Okay, that's the rotational losses. So that is the P rotational or P friction windage or mechanical losses. They're all the same meaning. The motor drives a mechanical load at a speed of 1170 RPM. So that is the speed now that the motor works at. And guys, you have to just have this in your mind. He has to specify a loading condition all the time. Otherwise, you will not be able to solve anything, because you trying to calculate or estimate the performance of the machine when it's applying a certain load. So he has to give you any information to just give you an idea about the load of the machine. So he can give you the output power of the machine, or can give you the torque developed by the machine, or give you the speed of the machine, because those all depends on the load. So the motor produces as much mechanical power as the load requires, and produce as much torque as the load requires, and the loads control the speed, because the higher the load, the lower the speed. So all those can be something that tells you information about the load, but you have to have anything of those. If it's missing at all, don't have anything to tell you anything about the load. If it didn't give you the output power or the output torque or the speed, he will be giving you here in the ratings the rated output power. He will be saying some sort, this motor is 100 horsepower or 100 or just 3000 watts motor. Here's in the ratings, and that means that is the rated output power of the machine, and you work at this rated output power unless anything else has been given to specify a specific load. Okay guys, but here is giving you the speed, so you don't need anything else. Okay, keep that in mind. And he's saying calculate the following information: the synchronous speed in RPMs, the slip, the line current, means the stator line current, input power, air gap power, torque developed, okay, the developed torque, the output power in horsepowers, and the efficiency. Okay, So those who need some sort of current calculations and power calculations, torque calculations, and efficiency, that is the typical demands in any problem that needs you to estimate the performance of a machine with a specific equivalent circuit parameters and at a certain load. Okay, guys? So here's the problem. Yeah, so that's what we need to do here. That's what we mean by modeling of machines, actually. So you just go to the lab and find the equivalent circuit parameters for a certain machine, and now you have a mathematical tool so you can use to predict the performance of the machine when dealing with any kind of a load. Okay? Isn't that magical? That's very, very good, because yeah, you don't need to actually go and experiment real life on the real machine and just sacrifice it if you don't, yeah, if it doesn't go well. But now you can just calculate it on a piece of paper. Okay, guys? Okay, let's try to solve this. First of all, just list your ratings. Okay, so the line-to-line voltage rated, which is used here, is 408 volts, and number of poles is 6. The frequency is 60 hertz. The machine is delta connected. The rotational losses is 1300 watts, and the speed of the machine, that means the rotor mechanical speed, is 1170 RPMs. By the way, here he didn't say anything about RC. It's not given here, the core losses resistance. That means you're dealing here with an approximate equivalent circuit, and he's assumed the core losses is lumped with the rotational losses. So this 1300 watts is both rotational losses and the core losses combined. Okay, guys? That means because RC is not given and core losses also, so he didn't give you any idea about the core losses or the RC, which is sort of represent the core losses. That means we are dealing with the approximate equivalent circuit, and that's very important to specify which kind of a circuit you're dealing with before you jump into anything. Okay, so draw it down for yourself. That's very important. R1, JX1, and here's JXM, because there is no RC or core losses given. That is JX2, and that is R2 over S. Okay, that is V1, and the current go here is I1, that is I2, and that is IM. Okay, guys? And now let's go and find out what he wants you to find. Number one, calculate me the synchronous speed in RPM. Okay? So number one, the synchronous speed, NS, which equals 120 F over P. So 120, the frequency is 60, and number of poles is 6. So it is 1200 RPMs. And that is your first demand here. Okay? As a double check, look, the mechanical speed given is 1170 RPM. And you know, for a motor operation, because we're dealing with a motor here, the mechanical speed has to be less than the synchronous speed, and not by a very big amount, slightly less than the synchronous speed, which is as given here, 1170. So it is around 30 RPMs below the synchronous speed. So that's good as a checker here. Again, that's my advice all the time. Look at the numbers. All the time they mean something. Yeah? So they mean something. So look at the numbers all the time, because it will tell you if you're just going in the right way or not. Okay, guys? So that is the demand number one. After this, he wants you to find him the slip. Be cautious. The slip, not the slip speed. Okay? The slip equals ns minus nm over ns. He wants you to find him the slip speed. It will be ns minus nm without dividing by ns. So they are different. The slip and the slip speed, they are not the same thing. Okay? So the slip speed is 1200 minus nm, it's 1170 over 1200. It will give you 0.025. That's your slip, and it's unitless because it's just speed divided by speed. Okay? Like you see in here again, that is a very small value, like we're seeing. most of the time the slip will be very small because the mechanical speed is very close to the synchronous speed for motor operation. Okay, guys? Okay. Then number 3, it wants you to find the line current. That means we need to calculate the stator current, so line current means the stator line current. Because when I say line current, that means the current that's moving into the line, and the line actually is the wire that's connecting your machine to the supply. Okay? And we know for induction machines, the stator is the one that's connected to the supply. So he didn't need to tell you which line current he wants. Is it the stator current or the rotor current? It is the stator current by definition. Okay, guys? So he wants you to find him the stator line current. So you can go again to the equivalent circuit here, R2 over S. And that is I1. But pay attention, that is a per phase equivalent circuit, single phase equivalent circuit. Like I'm saying all the time, everything here is per phase quantities. He wants you to find him the line current. So this current you're calculating here will be per phase value. You need to just find him the line one. So please keep that in mind. All the time, the most important thing to have in mind is make sure of your connection. It is here delta connection. That means the phase voltage equals the line-to-line voltage, while the phase current equals the line-to-line current divided by square root of 3. If you're talking about a Y connection, it will be vice versa. The phase voltage will be the line-to-line voltage divided by square root of 3, while the line current equals the phase current directly. Okay? Refer back to the lecture on three-phase circuits at the very beginning of the course, so we don't remember this information. Okay? So yeah, let's find out how to find those guys. So V phase equals V line, both of them equals 480 volts. That's it. So we need to find this current. How to find it? Just solve the circuit. It's a regular circuit, okay? So we'd find this current is by dividing this voltage by the total impedance of this circuit. So you need to find the impedance of this circuit. Simple as that. First you have those added together in series, and then in parallel with JXM, and the rest will be in series with R1 plus JX1. Okay, so first I will find Z2, which is R2 over S plus JX2. That is those guys, the rotor impedance, in parallel with JXM. I'm calling it Z2, okay, but yeah, you can call it anything. It's just a name. Okay. How to find this in parallel? You know the idea. It is just, that means R2 over S plus JX2 multiplied by JXM divided by the summation of them, R2 plus S over JX2 over JXM. Okay? And after you have this, the input impedance, or that is the total impedance of the circuit, called input impedance, will be Z2, which is just has given, plus R1 plus JX1. Okay? For this, you need to have a calculator that deals directly with complex numbers. Otherwise, you'll be taking ages to solve this. Okay? So it's not mandatory, but it's really, 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 really recommended. It will save you a lot of time. Okay? Everything here is given. You know the slip. We have already calculated here, so that is your slip, 0.025. And all those parameters given in the problem, so you can do this with your calculator to give you 9.33 plus J 4.16 ohms. That is the total impedance. So you can directly find I1. All these are vectors. It is V1 divided by Z input. V1 is 480 and its angle is 0 by default because that is the voltage. Divided by 9.33 plus J 4.16, and this will give you 42.9 minus J 19.1 amps. Okay? that is the phase value. Keep that in mind all the time, phase value. But he wants you to find him I1 line. Okay? And he wants you the line current, he wants you the magnitude by default. But actually you can find the magnitude and angle, it's up to you. Because that is a delta connection, the line current will equal square root of 3 by the magnitude of the phase current, which is I1 phase, yeah? So that is the square root of 3 by the magnitude of this current, it will be square root of 3 of the real part squared plus the imaginary part squared. Actually, you can do this with your calculator also. That will give you 81.3 amps. That is the magnitude, okay? If you want to find the angle of the current, it will be 10 minus 1 minus 19.1 over 42.9. Those guys. It is the imaginary part divided by the real part. It's how you do it by hand. Also, you can find it from the calculator right away. But I'm just giving you a glimpse of just remind you how to do it in case you don't have a calculator that can deal directly with it. Okay, guys? Okay. Okay. So by the way, this phase current here is 46.96 and angle minus 24 degrees angle. That is the phase current that you just can now find the magnitude of the line-to-line current by multiplying 46.96 by square root of 3. I'll give you 81.3. Okay, guys? Again, as something to have in mind, this angle is negative. That means it is lagging power factor. Okay, and all induction machines are lagging power factors actually. Okay, like we just discussed this before in synchronous machines, a lagging power factor here because it needs to get reactive power from the grid to build its own magnetic field because it doesn't have a separate source for excitation. Remember, for the synchronous machine, it has a separate source, DC source, going to the rotor, builds its excitation. So it has its own reactive power, and even it can be more to give it to the grid, and that's the whole point. But here for an induction machine, it doesn't have an external source or a separate source for excitation. It gets the excitation directly from the grid via its terminals. That's why it's always lagging power factor. So you need to double check this all the time. That is the current of the machine, the current going to the stator will be always have an angle which is negative. That means always most of the time having a negative imaginary part. Okay, that's something cool to look at. Okay, guys, nice. So that's the current, the input or line current. After this, he wants you to find him the input power. So that is the power going to the machine, which is obviously an electric power because that's a motor, yeah? So the input power equals 3 V phase I phase cosine theta, like we're saying. 3 V phase, all of those are magnitudes, please. Don't forget this because that's a power. It does not have an angle. So everything here, use a magnitude, okay? So that 3, V phase 480, I phase is here 46.96. Keep in mind that's the phase value, not the line value, which is 81.3 we just found. We need the phase quantity here, okay? Multiplied by cosine theta, theta is 24. It doesn't matter about the angle because the cosine doesn't matter what is positive angle or negative angle, okay? So this gives you this value 61.8 kilowatts. Okay, guys? That is your input power. That is the amount of power that the machine is taken from the source as an electric power for this loading condition. Okay? Cool. After this, he wants you to find him the air gap power. Okay? P air gap. How we can find it? So you can find it directly from the equation of it, which is 3I2 as a magnitude square R2 divided by the slip. But for this, you need to find I2, okay? How to find I2? it's easy, you can find it here from the circuit. That is I2. I1 is the total current going here, that is divided here to form you I2 and IM. So basically I2 will be I1, which is the current divider rule. Go back to your circuit courses again. It will be multiplied by JXM over JXM plus JX2 plus R2 over S. It's how to find I2 actually. So you can go over here and find I2 like this. All those are vectors, magnitude and angles. So you can find I2 and then find its magnitude and just plug it in here to find the air gap power. That's a method. The other method is looking at the power flow diagram. Remember? So the machine have here input power, and then you lose copper losses in the stator. And we should lose the core losses here, but we don't have core losses. It's lumped with the rotational losses at the end. Remember? Because that's an approximate equivalent circuit. So we don't have core losses here. The rest here, the air gap power. And then here you lose the copper losses in the rotor, P copper 2. And the rest will be your converted power or developed power. And again, you lose here the rotational losses and here plus the core losses because they are lumped together here in case of approximate equivalent circuit. And the rest will be P output, or call it P shaft, whatever you want to call it. Okay? So here I want you to find him P air gap, so it can be directly from here equal P input minus P copper in the stator, P copper 1. So it's up to you. You can find it directly from here. Go to the circuit and find I2 and use this equation directly, or find it from here. I prefer to go there because it doesn't want me to find him I2. Again, it's time saver. So P input minus P copper in the stator, which is 3, I1 as a magnitude squared times R1. You have everything here. You have P input, we've just calculated it. You have I1 as a magnitude, which is 46.96. And you have R1 given at the beginning. So that will give you P air gap to be 58.7 kilowatts. Okay, guys? So yeah, you can use it, or just you can solve it using both of those guys. Number 6, he wants you to find him the converted torque, or the motor torque, or the developed torque. They are all the same thing. Like we said, it can be calculated from P converted over omega m, or from P air gap over omega s. They give the same thing actually. Okay? And I like to go with P air gap over omega s because we just calculated P air gap, so we don't need to calculate anything else here. Okay? We just need to calculate omega s, which is 2 pi over 60 times the synchronous speed. That is in radian per second, and that is in RPMs. Do not forget this. So you have synchronous speed in your hand, which is 1200. Okay, we have just calculated at the beginning. So this is 2 pi over 60 times 1200. You plug it in here and you have just calculated P air gap, and this will give you the developed torque to be 467 Newton meters. Okay, guys? Okay. Number 7, he wants you to find him the shaft power here, yeah. The output power or the shaft power, the same thing, but in horsepowers, okay? So he wants you to find him P output in horsepower, okay? So P output is just your P converted minus P rotational, okay? Or yeah, for here it will be P rotational plus P core because they are lumped together or whatever. So here he just gave you P rotational at 1300 but didn't talk anything about P core. So he assumes they are lumped together, or he assumes that P core is neglected at all. So both of them work the same way. Anyways, okay? So that is given in the beginning to be 1300. So all we need is to find him the P converted. Okay. Again, how to find P converted? So you have multiple ways to do it again. P converted can be found from its own equation, which is 3i2 as a magnitude square r2 multiplied by 1 minus s over s. You have the slip, you have r2, but you need to calculate i2. So you can go and calculate i2 like we said before, and then you can find P converted like this directly. Or go back to the power flow and find it from P air gap minus P copper 2. So P converted equals P air gap minus P copper in the rotor. But again, you have P air gap in hand, but P copper in the rotor equals 3i2 as a magnitude squared r2. Again, you don't have i2. You can calculate it. But there is another way also to find P converted. I've given this a very precious tip, if you remember it, that you have this direct relation. P air gap to P copper rotor to P converted equal 1 to S to 1 minus S. That means those stuff, if you know any two of them, you can find the other two. That is P air gap, P copper 2, P converted, and the slip. We have here P air gap and have the slip. So we can find P copper 2 and P converted directly. We don't need to just go and calculate them. So P copper in the rotor directly equal the slip times air gap power, and P converted equals 1 minus the slip times the air gap power. Okay, guys? So yeah, go directly with this equation. So P converted equals 1 minus S times the air gap power, because we have the slip and have the P air gap, so we don't need to recalculate them. Okay, guys? That should be easy. And once you know this, go directly to find PO, which equals P converted minus P rotational, or P rotational plus P core, you know, so it is 1300. So this will give you 55.95 kilowatts, okay? But he wants it in horsepower, not in watts or kilowatts. If you remember, 1 horsepower equals 746 watts. Keep that in mind. So P output will equal 55.95 and multiplied by 10 to the power 3, because it's kilowatts, and divided by 746. This gives you around 75 horsepower. And that's what he wants you to do. Okay, guys? Last but not least, he wants you to find him the efficiency, okay? Equals P output over P input times 100. P output is 55.95 kilos over P input, which is 61.8 kilos, and multiply by 100 to gives you 88.9%. A good designed three-phase induction motor will have efficiency higher than 85%, okay? So that's a good motor. If you have this efficiency around 99.5% or something, that's something suspicious, because that's very, very high efficiency. And if you find it very low in terms of 35% or something, that's also very suspicious. So log back to your calculations, make sure everything is good. Otherwise, leave a note that is a poorly designed motor. It's having a very bad efficiency. Okay, guys? That's the whole thing. So yeah, we use the equivalent circuit parameters along with our equivalent circuit to actually estimate the performance of our motor, and that is very good. Okay, guys? Okay. Let me grab you another problem here. Yeah, should be this one. It is about the Thevenin equivalent circuit. Okay, so here he's saying for the machine in the previous example. When you say that's a machine for the previous example, he means same ratings and parameters. Okay, so it had the same ratings, voltage and number of poles and frequency and all that stuff, and had the same parameters R1, R2, X1, X2 and Xm. But that doesn't mean it doesn't have the same working conditions. So it doesn't mean it's working at the same speed or the same slip. They are different now, okay? So it's the same machine, but can be dealing with another load. So can be dealing with another speed, another slip, another power, all that stuff. But have the same ratings because that's something dedicated to the machine. And have the same equivalent circuit parameters because, again, that is something unique for the machine. Okay, guys? He wants you to find him the Thevenin circuit parameters and Thevenin voltage. So he wants you to find him the Thevenin equivalent circuit, okay? Okay. So, by the way, let's remind me of just, I want to remind you here about all the equivalent circuits we had before. That is R1, JX1, and here is RC and JXM, JX2, and R2 over S, and that is your exact equivalent circuit, okay? And you have another one here which is R1 JX1 and just JXM, and that is JX2 and R2 over S, and this is your approximate equivalent circuit, okay? And you have here this guy which is R Thevenin, JX Thevenin, JX2 and R2 over S, and this is Thevenin equivalent circuit, okay? By the way, here is V1, that is the supply voltage, but this guy here is V Thevenin, not V1. Just as a reminder for the different three circuits we're dealing with. So if you want you to find him the equivalent circuit parameters of Thevenin, which is R Thevenin, X Thevenin, and the voltage V Thevenin. Okay, guys? Fine. So we have derived this before, so we can directly use the equations. So for number one, we need to find the Thevenin voltage, which equals V1 multiplied by JXM divided by R1 plus JX1 plus XM. Refer back to the lecture when we just derived all of those. All of those are phase quantities again, don't forget. V1 is 480 and its angle is 0, because those are magnitudes and angles. Multiplied by JXM, it is given to be 30.74, divided by R1, which is 0.461, plus JX1, which is 0.51, plus XM, which is 30.74. By the way, I don't need to remind you guys about that XM and RC as very, very high compared to X1 and X2. Seen here, XM is 30.74, while X1 is 0.5. So again, yeah, they mean something, all the numbers. Okay, guys? So calculating this, and actually you want you to find him the magnitude of the voltage, or its magnitude and angle, it doesn't matter. So it is 472.1 volts. So it has the V Thevenin as a magnitude, and you can find angle actually because you're using the, use your calculator, and it will give you this as a magnitude and angle actually. But we're more concerned about the magnitude here. So actually, if you want you to find him, most of the time, if you want to find me Thevenin voltage, that means the magnitude of the voltage. Like in the previous example, when you want you to find him line current, that means you want you to find him the magnitude of the current, because that is the thing that matters most for an engineer out there. he wants to look at the magnitude, because that is a thing that is being translated into thermal amount and translated into settings for the control and protection devices and all that stuff. So we're more concerned about the magnitude, but actually you can find the magnitude and angle. It's up to you. Okay. So that is V Thevenin. We still need Z Thevenin, which actually will equal R Thevenin plus JX Thevenin. And this from the previous derivation also in the lecture equal JXM multiplied by R1 plus JX1 divided by R1 plus JX1 plus JXM. Again, refer back to the lecture if you don't remember how we derived this. Okay. Substituting for all of those, because they're all given at the beginning of the previous one, because they're the same parameters, so you can just find those easily to be 0.446 plus J.508 ohms. Obviously this will be your R Thevenin and this will be your X Thevenin. Okay, and you can draw the Thevenin equivalent circuit just fine here. So that is R Thevenin, which equals 0.446, and that is X Thevenin, which is 0.508, and that is your V Thevenin, which equals 472.1 volts, and that is your Thevenin equivalent circuit, which will be also after this connected to X2 and R2 over S. But this is Thevenin equivalent circuit actually, and that is what you need here. Okay, guys? Fine. After this, he wants you to find him the pullout slip. Okay? That means the slip, the pullout torque. That's a very, very important quantity to deal with. Okay? You remember, that is our torque speed curve, and that is your slip, and also speed on the same curve if you want. That's how it looks like generally, and that is your pullout torque and the corresponding slip, the pullout torque. That's important value because it just maps the highest value of a slip that can go, because that's corresponding to the highest value of torque. After this, you're going to breakdown zone. Okay, guys? We've also derived this back in the lecture. Refer back if you don't remember how we derived it. It equals R2 over square root of R Thevenin square plus X2 plus X Thevenin all squared. Okay. Also, you have everything here. You have R2 and X2 from the parameters of the machine given in the first problem, and R Thevenin and X Thevenin, we've just calculated them in the previous step. So everything here is in your hand. You can find SPO to be 0.191. Okay, guys? By the way, again, it's a tip. If you remember the slip in the previous problem, it was around 0.02 something, okay? And now that is the slip of the pullout torque. And you know that is the maximum slip that can go. So it makes sense that is higher than the slip you found in the first problem. And it should be a little bit much higher, actually, okay? If you find this SPO to be less than the slip you found in the previous problem, it will be very weird, because that means that the motor was working in the first problem beyond this value of SPO, and that means it was breaking down actually, and it doesn't make sense. Okay, so that's my all-time advice, to keep looking at the numbers. Okay, guys? Okay. Number 3 wants you to find him the pullout torque itself. So go here to find the pullout torque. Again, you can find it from the derived equation we found back in the lecture directly, but I like actually to go with the general torque speed characteristics equation. 3V Thevenin squared as a magnitude, of course, divided by R Thevenin plus R2 over S squared plus X2 plus X Thevenin squared R2 over S omega S. That is the general equation that can be used for any condition. Why I'm going with this here? Because it's more convenient. The torque here, if you want it to be the pullout torque, simply replace this slip by the slip of the pullout torque, and this slip by the slip of the pullout torque, and you have everything set now. Okay, guys? That easy. Again, everything here is known for you. We've calculated everything of those before, so that is 1482 Newton meter. Okay, guys? That is what we call the pullout torque, or the breakdown torque, okay, or the torque capability, because it just gives you how capable your machine is producing torque, because that is also what we call the maximum torque. So they are all names of the same thing here, guys. Okay? Okay. After this, find me the starting torque. Good. Okay. How you find the starting torque? Easy enough. Again, go to the same general torque speed characteristics. 3 V Thevenin as a magnitude squared divided by R Thevenin plus R2 over S squared plus X2 plus X Thevenin all squared multiplied by R2 over S omega S. Again, if you want to find any torque, find the corresponding slip. Easy enough. The starting torque corresponding to a speed equals 0, because that is a starting point. The machine didn't start yet, so the speed equals 0. And this corresponding to a slip equals 1, because you know the slip equals ns minus nm over ns. So if this is equals 0, then the slip equals 1. So that's easy. You want the starting torque, simply replace the slip by 1. Call the slip corresponding to the starting condition. Okay, guys? That's it. Again, everything is in hand here. That is the starting one, 649 Newton meter. Okay, guys? Okay. His last man here, using MATLAB or Excel or another computer program, plot the torque speed curve for slip in the range 0 to 1. We will not do this in this problem, and I will not be doing this on exam, but it's a very good exercise if you want to do it yourself. It's using the equation we just found here for the torque speed characteristics to actually plot the actual torque speed characteristics of the motor you're dealing with now. Okay, so you just use this equation we found here, this general torque speed characteristics, and just have everything substituted here. The V Thevenin, R Thevenin, R2, X2, X Thevenin, omega S, and just make the slip as a variable and just change this variable from 0 to 1 by a very small step, 0.01 or even less, and calculate the torque for each slip value and just plot them together to give you the corresponding torque speed curve of this particular motor. It's very fun. Try it yourself. Okay? For me, I'll just ask you to plot me a rough shape of the torque speed characteristics. So you want to go and just plot the torque speed characteristics of the motor roughly like this. For this case, it will look like this. Why? That is the pullout torque we calculated to be 1482, and the starting torque we calculated to equal 649. So like you see, the pullout torque is higher than the starting torque. That's why the torque speed curve looks like that. And that is a slip of the pullout torque, which is 0.191. That is this case we are dealing with because the pullout torque was higher than the starting torque. Okay? But for the sake of argument, what if we have another problem where the pullout torque equals the starting torque? Then your torque speed characteristics should look like this. Yeah? Because the pullout torque is the same as the starting torque. What about this if the pullout torque actually is less than the starting torque? For another problem. can this happen? Yeah, it can, sometimes. If you looked at the standardization page, which is actually a mandatory self-study page from the Pronite online materials I've just told you about in previous lectures, you'll just have actually seen motors have torque speed curves look like this. While you have, this is the pullout torque and this is your starting torque, and the starting torque is higher than the pullout torque actually. So yeah, it depends on the relationship between the torque, the pullout torque and the starting torque, which one of them is higher than the other, or which they are just equal. So you need to look at this before you plot the torque speed curve roughly like that. But if you want it to be just a precise torque speed curve, you should do it by some sort of a computer program, like we said, and it's just actually fun. I'll try it myself over you. Okay. So those are the three kind of problems you can encounter most of the time with three-phase induction motors. Okay, given the equivalent circuit parameters, and has to find out the motor performance by finding different currents and powers and power losses and efficiency, or to derive the Thevenin equivalent circuit and use it to find the pullout torque and the slip of the pullout torque and all that stuff. Or, like the last tutorial, is just to have the experimental data and use it to find the equivalent circuit parameters of the machine. Okay, guys? So those are mostly the types of problems you can encounter with three-phase induction motors. Okay, so I hope you just get some time to try to resolve the problems we had in the previous tutorial and this tutorial, along with your assignments about three-phase induction motors. Very, very important problems, and you can even find more examples in your recommended textbook by Chapman if you want. Okay, thank you guys so much for joining me today, and I'm looking forward to seeing you next time.